Okay, so please settle down. We can get started. Alright, so today we are going to be focusing on this topic, which is the control part of the processor. Okay? So what we did the last week and this week is going to combine together to sort of complete the entire MIPS processor at a very basic level. Okay, so let's look at where we stopped last week. Okay, so in last week, what we sort of went through was the entire complete data part of the processor. So when we say complete data part, what do we mean? It means we start from the instruction, right? We fetch the instruction from the memory, and when we fetch the instruction from the memory, we have the full 32 bits over here. Okay, and for the 32 bits that we have, we basically need to then channel the different sections of the instruction to different parts of the processor and make decisions along the way. Okay, so we saw that this position here, in almost all cases, this refers to your RS, correct? So that will, by default, give you one of the operands for your ALU. Okay, and we saw that the second operand for the ALU, okay, could come from your register or could come from the immediate value. Okay, so in your register side, you also need to make a decision whether the second register is going to be read, or is it the second RT bits here is referring to the target register. Okay, so whether it was going to be a RS type, a R type instruction or I type instruction, then you would decide whether the 20 bits to 20 to 16 should come here or should come to the right register. So what we also saw was that regardless of whether it is going to be R type or I type, bit 20 to 16, for example, will still come here, which means that whatever that is specified in bit 20 to 16 will also come out here. Correct? And at the same time, you are also going to look at bits 15 to 11, okay, as a possible register for your write. Okay, so this could be your RD register, okay, or it could have been also part of your 16-bit immediate value. But whatever is the case, this will come here, and your register destination will then make a decision which bits will be sent over here. Okay. Similarly, over on the ALU side, there is some data that is going to come here, and the lower 16 bits will get sign extended and also come here. Alright, then you have a multiplexer there to decide which data will be then channeled to my ALU to do the operation. Okay, and finally, when I get the ALU result, what is this result signify? Correct? Is it actually the answer that I'm looking for? That means, is it like an add instruction, or was it a load word type of instruction where the ALU operation is actually giving me the address? Correct? So we do not know, but anyway, whatever is the value that comes out, I will still go and activate my memory. Correct? So even if it was an add instruction, okay, to say S0, S1, S2, where we are dealing with all data, and the final result is going to be stored inside a register, this final result will still be sent to my data memory because it is already hardwired there, correct? Okay, it is still connected. Okay, and at the same time, that result will also come here. Then I need to make a decision whether I want the data or the result from the ALU or is it the output from the memory to be sent back to the register. Correct? So I have another selector here called mem to register. Okay, and eventually one of this will be sent back, okay, to my write data here. Okay, do I need to write or do not? I do not need to write. Also depend on a pin here called register write. Okay, so last week's lecture material, please go through again to understand the flow. Okay, if a R-type instruction come in, what will happen? What is the first step? What is the second step? How will the bits propagate through the processor? Okay, so you sort of understand how your processor is making decisions. And the most critical part of this whole thing is what? The most critical part of this whole thing to work is all your control signals, because these signals here are the ones that actually tell us or tell the processor what to do. Correct? Because along the way, when I need to make all the decisions, these control signals are the ones that are telling the processor, at this side from the register, take the bits from 15 to 11. At the ALU side, take the 16-bit immediate value. After the ALU come out, don't take the ALU result, take the data from the memory. So all this is only decided through the control signals. Okay, so these play a very important role in our processor. Okay, and that is what we are going to be looking at in today's lecture. So this is a snapshot of your various control signals and what are their purpose. Okay, so we know that register destination is to select where I'm going to write to. Register write is just a pin, correct, whether I enable or disable. Okay, it does not specifically channel data anywhere, but it just to give me a selection option of whether I need to update the register file or do not need to update the register file. Okay, ALU source is to select the second operand. Why second operand? Because your first operand is always fixed. Your first operand is always from your RD1, right, your register file. It's only the second operand that we need to make a decision whether it is from the register file or from your immediate value. Okay, so that is where your ALU source comes in. This ALU control is telling the ALU what needs to be done here, correct? Okay, so this 4-bit here that you see will tell the ALU what operation should I do. Is it an add? Is it an AND? Is it an OR? Okay, and memory read and memory write again are to enable. So they are not channeling data, but they are giving some control to the memory block to say whether right now should the memory be in a write mode or should I be in a read mode. Okay, so memory, if you look at the hardware, okay, you have address bus. Okay. Okay, so memory, if you look at it, okay, you have your address bus, okay, you have a data bus, okay, and then you have your control signals. So the control signals in most cases is your read and write. Okay, in most processors, usually they have a single pin and then they will toggle between low or high. Okay. But in our case, we assume that you have two different pins for read and write capability. Okay, so when I select, so even though I put some value inside here, okay, so for example, even if I put some value here, okay, I put some value here, then I still need to select one of these options. Alright, I need to tell the memory chip whether this address I'm going to read from this address or I'm going to write to this address. So these are all the control lines that you need to connect. Okay, and all this goes towards where? Goes towards your microprocessor. Okay, so in your microprocessor, you have your address bus, your data bus, your control lines, and you need to then come up with a logic, correct? A firmware to interface with this memory hardware device. Okay, so let's come back here. Okay, memory to register here is to decide whether I am going to select the output from the ALU block or I'm going to select the output from the memory block. Okay, so at this point of time, what should I do? Should I take the data from the ALU result, or should I take the data from the memory? And the last one here is the PC source. Select the next PC value. Okay, so by default, whenever I fetch an instruction come out, the PC through this hardware block already generates the PC plus 4. Now that is by hardware. At the same time, I know that I have branch instructions, so I also need to cater to that. So what I need to do, I need to take the lower 16 bits, do the sign extension, left shift by 2 bits, right? Because this is the number of lines, correct? So this left shift by 2 is to multiply by 4, so I know the actual number of bytes to offset. So I need to stand by this together with my PC plus 4 and provide a multiplexer, correct? So this PC source will then need to make a decision, correct, between should it be 0 or 1, depending on whether I am executing a normal instruction or whether I'm executing a branch instruction and the branch is supposed to be taken. Okay, so these are the signals. Okay, so the main idea of controlling these control signals is to again decide the format or the flow of the data through your processor. Okay, so we're going to look at that, okay, in this next few slides here. So for example, if I say I have a R-type instruction, what does that mean? Okay, my register destination should be 1. Okay, why should it be 1? Now we will look at that in a while. Okay, so let's look at the control unit, okay, and let's see how we can design it. So this control unit here, you can see right now, is a block that is now going to be providing me with all the output signal that I need. So this register destination, register write, ALU control, ALU source, mem write, mem read, and mem to register are all coming out from this control block. Okay, this control block will make a decision on the logic levels on all these different pins. Okay, so that it knows, okay, this is a R-type instruction, these are the pins I should be setting or clearing. If this is a branch instruction, these are the bits I should set and clear. Okay, so it needs to now make some decisions, okay, for all these pins. So what we need to do is we need to look at the opcode, okay, because we know the opcode is giving us an idea of the type of instruction that we have. And for R-type instruction, we also have the last 6 bits, which is the function field. Okay, so looking at the opcode and looking at the function field, we can then sort of decide how these control signals should be set. So this gives us an overview of the subset of the instruction that we are looking at. If you look at R-type instructions, okay, these are the different instructions. Okay, so in this set of notes here, we are not going to look at all the possible instructions. Okay, that it will be too much to cover. So we're just looking at a subset of instructions, and then we are looking at how we are going to design the control unit to cater to this subset of instructions. So in this case, the subset is the R-type instructions, which are these, okay, and the I-type instructions, which are these. Okay, we're just looking at a subset of the instruction set to have an idea on how the control unit can be designed. Now, if I look at this subset, okay, what can we observe? So we observe that in these R-type instructions, all my opcode is 0, correct? Okay, and I can use the function field, for example, to differentiate. Okay, differentiate the type of instruction that I have. And in my load word, store word, I have some values here that I can also look at to differentiate between whether it's a R-type and within the I-type, is it a load word, store word, or whether it's a branch. Okay, now let's look a bit at the multiplexer values and how we do the mapping. As we know, a multiplexer is nothing more than having multiple inputs, and then you have a selector. So if I have 2 input, then it's just 1 bit selector, right? Because the only 2 values are either 0 or 1, correct? So if I say the signal is 0, then the 0 will go through. If I say the signal is 1, then the 1 will go through. So at any point of time, depending on the multiplexer selector input, one of the input will be selected to go through. So in register destination, how will I connect it? So I know that instruction bits 20 to 16 here, okay, will come to the top, and instruction 15 to 11 will come to the bottom here. Now if I say that a multiplexer is numbered as 0 on top and 1 below, what does that mean? It means that when I am doing a R-type instruction, okay, if I say I'm having a R-type instruction, okay, so if I say add S0, S1, S2, okay, then if I were to look at my instruction encoding, I have my opcode, okay, my RS, RT, and RD here, correct? Okay, so the last, this bit here is my write register, correct? Is my write register. So what I want to say is my write register is specified by instruction position 15 to 11, correct? Which translate to this. Okay, so for R-type instruction, then I will say that my register destination should be 1, okay, for R-type. Okay, when register destination is set to 1 for R-type instruction, what will happen? Instruction from the 32-bit instruction, bit 15 to 11 will be selected to go through the multiplexer and to send to the register file as the register I want to write to. So that is how you decide the mapping between 0 and 1 and the selector logic value. Register write is just a single bit to tell us whether we want to write to register or don't want to write to register. Okay? Why we need this bit here? Because there will always be something here. Correct? There can always be something there, which could be the data that is from the previous instruction, alright, or could be some random value which we do not know. And similarly, there will always be something over here as well. Why? Because a previous instruction, okay, would have channeled the data back here, correct? Okay, so there will always be something at the write register pin. There will always be something at the write data pin. But it's not always we want to write back to the register. So we need a pin, okay, to tell us whether this data and this write register is valid, and now I need to update the register. Just like your memory, correct? There will always be something at the address, there will always be something at the data. But I need to activate memory write or memory read correctly to tell the memory block whether I'm going to do a write or whether I'm going to do a read or I don't need to do anything. Same thing over here. So there will always be something present at the bits here, at the pins here. So the register write is to indicate that at this point of time, the write data is valid, the write register is correct, so you can go and update. Okay, so that is why you need a register write pin. So it's just a 0 or 1 to tell the processor whether you're going to update or not going to update. ALU source. Okay, so ALU source is to differentiate between two possible inputs. Okay, one is your read, register read data 2, which is this. And so you can see that this is connected to the top here, so this is 0, and this sign extended immediate value is connected to the 1. Okay, so it means that if ALU source is 0, then I take from here. Okay, if I say that ALU source is 1, then I take the sign immediate value. Okay, so for example, if I say R-type instruction, okay, definitely I will take from my read register 2, alright? If it was a I-type instruction, okay, so for example, if it's a I type instruction which is doing some operation, then I also need to, then I will take from the 16-bit sign extended value over here. Okay, so this 0 and 1 is to tell us whether the second ALU source is coming from the register or is going to come from the sign extended immediate value. Memory read, like I said just now, is just to tell the memory block whether the address right now that I have provided at the address bus is the address that I want to read data from. Okay, so once I supply an address and I activate the memory read pin, then I am telling the memory block that I want to read from this memory address. So that data will come out here. Okay, so that is your memory read. Similarly for memory write, okay, if I provide the address here and I provide the data here and I activate this pin memory write, then I'm telling the memory block that whatever is my address bus is the address I want to write to. The data bus has the data, so now we go and update the memory once the memory write pin is activated. Okay, so this is important here. The mem to register. Okay, the mem to register is also has a multiplexer here. Okay, but this multiplexer is to do what? Is to decide whether the output that I'm interested in is coming from the ALU block or is it going to come from the memory. Okay, is it going to come from ALU block or is it going to come from memory? So I have two input. One is from the memory and the other is the ALU output. Okay, and one of these will be selected out. Okay, to go back to my write data here. Okay, so if I had, my instruction was the add instruction. Okay, so I would have done an add operation, and the ALU result from the add is available here now, and it is currently at this multiplexer here, correct? Okay, and if I want this result to go through, my mem to register in this case should be 0. Okay, so when I say mem to register is 0, then the data from here will go through. Okay, when I say that my instruction is, for example, a load word instruction, okay, so what is happening? If I say this was the load word instruction, then my ALU would have done a add operation, correct? And that add operation would have activated the memory address, and I would have also triggered the memory read pin, and that data in that memory location would have been available here. Correct? So in this case, my mem to register should be 1. Okay, so the data from my memory is the one that will go through here. Okay, so why do we say this is swap? Because if you look back at the previous ALU source and so on, okay, the 0 is on top, 1 is below, correct? Whereas here, in this case, the 0 is below, 1 is on top. Okay? So of course, when you look at this, you think, why again they make your life so difficult, correct? Why didn't they just, so to solve this problem is what? All they need to do is change the name, correct? If I just say ALU to register, then it becomes 0 on top, 1 below, correct? Because the fellow who decided this say he wants to call it mem to register, all of us have to suffer, correct? Okay? So in fact, if I just go and change this name to say ALU to register, what does that mean? When it's 1, then the ALU data should go through, correct? If it's 0, then it should be the memory data that go through. Okay? The reason why they go and put it this way is because they call it mem to register. Okay? So when you say mem to register, the intuition is what? If I say 1, that means the data from the memory go to register, correct? So all you need to do is just improve the English, correct? Say ALU to register, then the whole problem is solved. But unfortunately, they decided to say mem to register. Okay, so that is why it becomes swap. Okay, so why I'm stressing this? Because this is again another common exam question. We will purposely say, your friend designed this processor, he mixed up the multiplexer, can you figure out what went wrong? So you need to go and look at all these multiplexer pin and see what is the configuration and whether it's correct or wrong. Okay, so this is, again, it's just a convention. Because of the name, the 1 become on top, the 0 become below. If it was ALU to register, then this would be 0, this would be 1, and this would be from my ALU, and this would be from my memory. Then it would have followed the same convention. Okay, the next one is your PC source. So in PC source, what are we doing? We are differentiating between two possible inputs, correct? Okay, one input is what? Your PC plus 4, which is your default value. Okay, the other one is your new branch instruction based on the offset together with your PC plus 4. Okay, but one thing is, this PC source signal, can it be just directly generated from your control block? Cannot. Why? Because your control block can only tell you that this is a branch instruction. Correct? But it cannot tell you whether the branch is going to be taken or not. Correct? The decision on whether the branch is to be taken or not is only obtained from the ALU. Correct? Only after I compare the two numbers, then I can make a decision whether the branch is to be taken or not. Okay, and that is from the E0 pin over here. Okay, this E0 pin basically will compare, okay, basically do a subtraction, correct, between the two numbers to say whether it is match or no match. So even though the control unit can tell me it's a branch instruction, only the ALU can tell me the outcome of the comparison, whether I'm supposed to take or not supposed to take the branch. So the PC source has to be modified to include one more AND gate there. Okay, why this AND gate? Because I need to check two things. Whether is it 0, that means the two values are matched, correct? And the second thing is whether it is a branch instruction. So only if both these conditions satisfied, then I say that I select. Okay, so the 1 is below, if not it will become 0. Okay, 0 means then I go to the default next line instruction. Okay, so you can see that your multiplexer, all of it is 0 and 1 except the last multiplexer, which is for your mem to register, which is the reverse connection. Okay, so at this point of time, what have we done? We have basically gone through all your signals that you need to generate except for the ALU control. Now all the other signals, we have sort of looked at it to see how it relates, okay, to the different type of instructions. So we know if R-type do what, if it's I-type do what. Okay, only ALU control is left. Okay, and we saw that except for the branch instruction, the rest of it can be decided immediately with the opcode. Just by looking at the opcode, I will be able to know whether I need to do a R-type instruction or whether it's a I-type instruction. Okay, so now I'm going to look at the ALU control. So the ALU control, what will it do? It will take the 6-bit opcode. Okay, it will take the 6-bit opcode and do what? Okay, so we need to now use this 6-bit opcode to decide on some of the ALU operations that we're going to do. Okay, so let's look at how we're going to do that. So the ALU control, we say it is 4 bits. This 4 bit come from where? This 4 bit come from here. These are the 4 bits that we are going to connect to the ALU control, and this 4 bit is coming from where? It is supposed to come from the control unit. Okay, so let's look at it. So this ALU control, the 4 bits, this is the mapping. Okay, so 0, 0, 0, 0 is n and so on. Okay. Now, for this mapping, okay, that we have and the functions that we have, let's look at how we can design a simplified 1-bit ALU. Okay, so this is a simplified 1-bit ALU. Okay, so you can see there are two inputs here, A and B. Okay, this is 1 bit only. This is 1 bit out of the full 32 bits. Okay, so for example, if I say I design a 4-bit adder. Okay, so this is just 1 bit. Okay, so let me draw 1 bit. So this is maybe A and B. Okay, so this is bit 0, this is bit 1, bit 2, and bit 3, for example. Okay, so now what I'm showing, what they have drawn here is just a single bit block. Okay, that will look at the 1 bit at a time. Okay, so inside this block, what do you see? You see A, you see B, and you see 4 control lines: A invert, B invert, C in, and the operation. Okay, so let's see how we can make use of this. Okay. Okay, let's see how we can relate this truth table to the hardware that you see here. Now, let's look at the first operation here. I want to do an AND operation. Okay. So let's say my AND operation for A and B is 1 1 0 1 1 1 0 0. Okay, so now I'm looking at just 1 bit, correct? Only 1 bit. So if I look at A and B, 1 comes here, 0 comes here. Correct? Okay? And my A invert is 0, B invert is 0. So this is your 0, 1, 0, 1. This is a multiplexer input selector. Okay? So if A invert is 0, what will go through? If A invert is 0 means your A will go through, correct? A invert is 0, your A will go through. If your B invert is also 0, then your B will go through. Okay? So the first A invert and B invert is to say which one goes through to the next stage. Okay, so if I say A invert 0, B invert 0, then A and B directly go through. I don't invert it, correct? It directly goes through to the next stage. In the next stage, which is here, what do you see? You see 3 hardware operations concurrently, correct? 3 hardware operations concurrently. You have an AND operation, you have an OR operation, and you have a ADD operation. 3 hardware operations concurrently. That means what? That means at any point of time, I will have 3 output standby for me, correct? The 3 output is what? A and B, A or B, A plus B, correct? So I have 3 output automatically generated for me, okay, and presented to the multiplexer here. This is a multiplexer with 2 selector input pins, correct? Okay, that means the possible values is 0, 0, 0, 1, 1, 0, 1, 1, correct? Okay, so if it was 0, 0, the first line will go through, correct? 0, 1, the second line, 1, 0, the third line. 1, 1 is not used. Right? 2 input, 2 selector pins means I can have 4 input, okay, for a multiplexer. So since my operation here is 0, 0, that means the first one, which is the AND, will go through, correct? Okay, and this one will go to the output. Okay, if this was a OR operation, what will happen? Okay, in this case, so A invert and B invert is still 0 and 0, but my operation is 0, 1, correct? Which means the second one will go through. Okay, and if it was an ADD, okay, then it will be 1, 0, which is the third one will go through. correct? Okay, now let's look at subtract. So subtract, what must I do? So subtract, what do we do in the tutorial? When we say you want to subtract two numbers, it is the equivalent of adding the complement, correct? We add the complement. So that is why you can see that for subtract, your A is still 0, but my B invert is 1. So if my B invert become 1, okay, if my B invert become 1, what will happen? My B will now go through my inverter here. Okay, so the bit will become flipped, and that B inverter will now go through here. Okay. So that is why when my last two bit, which is 1, 0, will select the add operation here. So the result will be A plus minus B, correct? A plus minus B. Can you see? Okay, so we haven't gone through all this hardware, which is actually the second half of the semester. But roughly you should look at the gates to understand. So these are three basic gates only: AND gate, OR gate, or inverter. Multiplexer we have seen. Okay, so the three basic gates are the AND gate, OR gate, and inverter. Okay, any question? All okay? So is this correct or wrong? Nobody asked me the important question. I'm waiting for somebody to ask me the important question. Is this correct or not? Should I reserve for midterm? Okay? What is missing? What have I done? I have done A add with invert of B, correct? But A add with invert of B is what? Invert of B is just the 1's complement, correct? It's supposed to be 2's complement, correct? Our computing systems are supposed to be based on 2's complement. But if I say A add with invert of B, it is equivalent to A plus the 1's complement of B, correct? Okay, so where does the 2's complement come in? What must I do? I must add one more 1 here, correct? After I flip, I must add one more 1, correct? Where does the one more 1 come in? From my carry in of my least significant bit. Okay, so rightfully this is one block, this is another block, this is another block. But for the very first block, I need to bring in a carry in for the subtraction. Okay, to make sure it's a 2's complement number. Correct? If not, it becomes a 1's complement addition or subtraction, correct? Okay, so the 2's complement, to make it 2's complement, the lowest significant bit, I must still have one more additional carry in bit set to 1. Okay, the other carry in bit what? So this carry out, the carry out of the least significant bit will propagate as the carry in of the next bit and so on, correct? Just like how you do in pen and paper, the hardware must do it, correct? In pen and paper, we say 1, 1, 0, when we say 1, 1, 0, 1, and we say 0, then we carry 1 over, correct? Okay, so this carry is what? The carry in. Okay, so the carry in of the next bit, carry in of the next bit. Okay, so the hardware is all hardwired together. The hardware is all wired up together for you. Okay, so from one bit to the next bit and so on. Okay, so that is how the 1-bit ALU works. Okay, so just for your own information, this one not tested, but just for your own information only. So you can see what's the problem here. If I say I have a 32-bit number, add to a 32-bit number, can you imagine how slow it's going to be? Because even though I can add all of this in a few nanoseconds, correct? One clock cycle, I can get the answer. But what's the problem? The problem is I need to wait for very long, correct? For the carry to propagate until it go to the 31st bit and then I get the final carry, then I know the answer. Correct? So if you look at it from a hardware perspective, it's actually a very, very inefficient way of doing adding. Okay, so in terms of hardware itself, just for adder, there's a lot of variation in hardware. Okay, there is carry look ahead adder, there is prefix adder, so there's a lot of variation in adder. Okay, so even though we say add in MIPS, the actual hardware can be very, very different. Okay, depending on how efficiently it is designed. Okay, but anyway, that is just for your information only, don't worry. Okay, so let's come back to this. So just now what we look at is the 1-bit ALU, 1-bit ALU. So we just saw how a single bit block can be, a single bit will sort of do the various operation of AND, or subtract, or whatever. Okay, now what we need to do, we know that this is what we need to send to the ALU hardware. Okay, this ALU control here is what we need to send to the ALU block. So if we go back to the previous diagram here, this is what we are trying to do. The 4 bits that we have is the 4 bits actually going to the ALU block to tell the ALU what is the operation I want to do. Okay, but this ALU control, this 4-bit ALU control must be generated from where? So I have 6-bit opcode, and I have another 6-bit function field. 6-bit opcode and 6-bit function field. So let me see how I'm going to make use of that. Okay, so one is called a brute force approach. Okay, brute force approach is what? That means you try to look at all the bits. Okay, and then you come up with a check, a hardware check to say, okay, if my opcode is all 0 and my function field is 0, 1, 1, 1, 0, 0, then this is add. Correct? Then you say opcode is 0, 0, 0 and my function field is 1, 1, 1, 1, then this is subtract, something like that. Okay, so in a brute force approach means you just say you look at all the bits, correct? And then you make a decision. Okay? The other way is the multi-level decoding. That means you try to do some simplification to try and break it down to a few simpler way of checking to minimize the hardware. Okay, so we're going to do that second approach. Okay, so the first step that we're going to do is we're going to generate a 2-bit ALU op known as a 2-bit signal known as ALU op, and the main purpose of this ALU op is to differentiate between 3 types of instructions. And the 3 types of instructions are your memory access instructions, which is a load word, store word, your branch instruction, and your R-type instruction. Okay? And using the 2 bits here, I combine with my function field to generate the 4-bit. Okay? So what am I doing? I'm going to use the opcode. So the opcode, okay, I'm going to send it to my control block. Okay, and from the control block, I'm going to generate the ALU op, which is 2 bits. And then these 2 bits here, so this is 6 bits here, my ALU op is 2 bits, and I'm going to combine it together with my function field, which is 6 bits, to generate my final 4-bit, which is my ALU control. Okay, why we are doing it this way? Why not just the brute force approach? Then if I do that, then I need to look at all 12 bits, and my hardware is going to get very complicated. Okay, not say complicated, but it's an inefficient use of hardware. Okay, because you're just doing a lot of check whether this bit is 1, this bit is 0, this bit is 1, and so on. Okay, so instead of that, we are going to sort of simplify it to first look at opcode. From opcode 6-bit, we shrink it down to 2-bit, and then we combine with the function field. Okay, and then we combine the function field to look at the ALU control. Okay, so that is the overall idea that we have. Okay, to generate and combine the bits together. Okay, so this ALU op, the 2-bit is this. Okay, so I can either have 0, 0 if it's memory access, 0, 1 for branch, and 1, 0 for the ALU operations here. Okay, and then I combine with the 6-bit function field to generate my 4 bits here. Okay, and these 4 bits are the bits over here to tell the exact operation that I want. Okay, so let's take a break here. I see hence a sense of sigh of relief. Okay, we'll take a break. We'll come back in 10 minutes time. Okay, and then we will carry on. And just to give you an incentive to come back, we were going to discuss some of the midterm, what is going to come on and so on, so that you don't run away. Yeah? Okay, so we'll come back in 10 minutes time. Huh?
For this is 1 bit of this, right? So it's like 1 square like that, right?
This is one.
This is 1 bit of the 32-bit number we're going to do the operation. Oh, so is the A and B is A and B. Oh, so it's not telling the ALU what operation you're supposed to do. That is these 4 bits. Oh, these 4 bits. Yeah, these 4 bits are these 4 bits. Oh, okay. So I thought it was like these 4 bits, then you need to split it. No.
When you have an ALU, for example, in this case, let's say we're trying to do an AND operation, and somehow the 2 inputs for the ALU arrive before the ALU control is done generating the AND. How does the ALU know this is not the input I want? I need to wait a bit. Like, this is not going to be an AND operation, right? Because it's going to receive 0, 0, 0, 0.
Right. So basically, all of that is part of the internal microprocessor timing.
So it can time every single substage. Right? So, but I thought that's only for pipeline processors.
True, this will be doing that, but for a single cycle, basically, in a sense, it doesn't matter whether the
Order of the arrivals.
is different, because as long as you know how much time to wait before everything happens.
Until the correct one is generated. Then you take the correct one
Yes.
and the load one. Okay, I see. Thank you.
So, assuming the two input coming is 1 bit by 1 bit coming, right? So let's say this one is 32 bit, so you'll be 1 bit, 1 bit, and also 32 bit, 1 bit, 1 bit.
No, it's not one bit.
Or it's the whole chunk.
This is just one bit. Then the same block will repeat itself at the same time.
So, like let's say the integer that I'm going to add is 32 bit, 32 bit. It's not processing 1 bit at a time after 32 bit.
Each block is only one bit.
Like, for example, 1101 and 1101, right? So only one comes in here and one comes in here.
Yes.
Then after the whole cycle finish, then you'll do 0 and 0 here.
No. It will automatically do all the bits. But because of a normal adder, then it will, in the normal add operation, then you will wait because the carry has been propagated. Okay, but I'll explain the whole class again. But basically, you just remember that this is 32 bit, alright? But each block, this is 1 bit, that's why you put 1 bit at a time. So this is only 1 bit of the 32 bits.
The result.
The ALU. Your ALU is 32 bit ALU, correct? But this 32 bit ALU is obtained from combining 32 such blocks together. Okay, so I want to do 32 bit operation. Alright, but the 32 bit operation is obtained by creating an equivalent block for a 1 bit ALU. It's just like Lego block. If I want to build a tower, you know Lego block, right? If I want to build a tower, what can I do?
Stack one by one.
Correct, exactly. So if I stack 32 blocks together, then I have 32 bit long tower, right? So one tower block is 1 bit. So when I stack 32 together, I get a 32 bit block.
Oh, so the ALU itself is 32 bits already, then like inside is starting all zeros.
You can assume something.
Then based on this number of these different bits, you'll change the bits in the ALU itself.
You will change the operation that is required. The operation. See, these 4 bits are telling the ALU whether I'm going to do a AND operation or OR operation or whatever.
Yeah.
So the data is A and B coming in from the register. Alright? Then I have this full 32 bit. Okay, and I map to all the 32 bits here. Alright?
But how do you map the A and B to the 32 bits?
That means each bit will go to one of the 1 bit ALU.
Oh, okay. So the ALU have 32 of these squares, then
Yes.
these two, so it's like 1101 and 1101, right? Then this is 1 square, this is 1 square.
Correct.
Okay. Then how I know which, when,
Correct. So that's where these 4 bits come in.
so if it's 1, you'll take top one,
Yes.
0 take middle one.
0 is on top, 1 is.
Oh, same for here also.
Yes.
0 is on top. Is it always like that?
General convention is start from 0 on top. Okay, so let me explain this again, in case you did not get the idea of the 1 bit ALU. Okay, so what do we mean by 1 bit ALU? Okay, when we are talking about 32 bits. Okay, so you treat this as a single. Okay, so when you say this is a 1 bit ALU, okay, what are we doing? We are saying that, okay, you have 2 numbers here, okay, A and another number B. This A and B come from where? These A and B are the 2 inputs to the ALU, correct? Are the 2 numbers, okay? So it could have been your 2 register, or it could be 1 register or 1 immediate, you do not know. But you know that each of it is 32 bits. Okay. So when these 32 bits are sent to the ALU, this ALU is actually a 32-bit ALU, correct? But this 32-bit ALU is composed of 32 1-bit ALUs. Okay, 32 1-bit ALU. That means this is bit 0, bit 0, bit 1, bit 1, correct? So what will happen? The bit 0 will come here, A0, the bit 0 will come here. Okay? So when I supply the A0 and B0 to this bit, similarly, I have the next 1-bit ALU. Okay? And this is from the next bit, which is your A1. And this is from the next bit, which is your B1. Okay? So inside the ALU, you have 32 1-bit ALU stacked together. Okay? And what are you doing? For each of these ALU, you are providing 4 control inputs, which is your A invert, B invert, and your operation. Okay, so for each of these blocks, you are supplying your A invert, B invert, and your 2-bit operation, okay, together with your carry in. Okay, together with your carry in here. And each ALU block, what does it generate? It generates 2 outputs. One is the result, and the other is your C out, your carry out. Okay, that means at the output side, I have 1, which is my let me call it Y0, okay, Y1, and my C out, C out. Okay? So what do you see? When I supply a 32-bit, 2 32-bit numbers, okay, each bit goes to each of these 1-bit ALU, okay, all the way, okay, up to my last one, okay, which is my A31 and B31. Okay, so it propagates all the way, all 1-bit ALUs. Okay, and what do you do for each of these 1-bit ALU? You provide your 4-bit control signals here. So if this was a AND operation, okay, let's assume this is an AND operation, then what would have happened? I would have told the control bits to be set to what? 0, 0, 0, 0, correct? Okay? So what you would have seen here is 0, 0, 0, 0, and I would have done the AND operation here, and I would have gotten the output here. Correct? So if I were to say that my input is, for example, 0, 1, 1, 1, 1, 0, 1, 1, then I would have done the AND operation. Okay, and the output would have been obtained after how much delay? After the delay of a single bit ALU, correct? Because all the bits can do the AND operation concurrently at the same time. There is no dependency for any higher level bit on a lower level bit. Correct? If I were to do an AND operation, all 32 bits A and B can do the AND at bitwise level at the same clock cycle. Correct? And the output is available immediately. Okay, because there is no dependency from a higher level bit towards a lower level bit. Whereas, if I were to do a add operation, okay, if I do an add operation, I take A and B add together, but I always have to wait for the carry in of the previous bit to propagate to the next bit. Then the operation is complete. Correct? So even though the A1 plus B1 is available here, this carry out can only be obtained after this carry out come in here. Correct? Then the operation is complete. Okay, similarly, this one must propagate to the next one and so on. Okay? So for an add operation, for example, the total time that it takes would be the time of each ALU multiplied by 32, correct? Because I need to wait for all 32 bits to be completed before the final carry out is generated. Okay, and the final Y31 is generated. Okay, so that is the idea of the 1-bit ALU. So your 32-bit ALU is just 32 1-bit ALUs combined together. Okay, so that is how your hardware inside is designed. Okay, this is just one possible design. Like I said, you can have a lot of variation to the design depending on how you want to sort of create your processor. Okay, so that is beyond the scope, but this is just to understand, so you understand how the lower level integration is like. Alright, so now coming back to this, we said that we are now going to use the control signals, the 6-bit control signal, to generate a 2-bit ALU op, which is this, to differentiate between memory instruction, branch instruction, and R-type instruction. And then we are going to look at the lower 6 bits, okay, together with these 2 bits here, combined together to another block known as the ALU control block. And the objective of this ALU control block is to generate these 4 bits. So these 4 bits go to where? These 4 bits are going to your 1-bit ALU, all the 1-bit ALUs inside, that 32-bit ALU block. Okay, so let's look at how we can generate this ALU control signal here. Okay, so these are the different instructions, your load and store, your branch, and followed by the 5 different R-type instructions here. Okay, so this ALU op, this is what is given to you over here. So we are saying that if I say ALU op is 00, then it is a memory instruction. If I say is 01, then it's a branch instruction. If I say is 10, then it is an R-type instruction. So that is the mapping that is done from the opcode itself. And this is from the opcode. So if you look back here, just using the 6-bit opcode here, I directly translate to my ALU op. Now the function field. The function field is only available for R-type instructions, correct? Okay, so for memory instruction and branch instructions, there is no function field to look at. Okay, and this function field, this data we get from where? From the instruction set. So from your MIPS instruction set, we know all the different function fields for the different type of instructions that we have. And this is the ALU control that we want to generate. Okay, so we have 2 inputs, which is the ALU op and the function field, and this is the output. The ALU control is the output that you want to generate. Okay, so let's look at how we can go about doing this. Okay, so if I want to put all the bit pattern inside, okay, what do you see? Okay, so it looks scary, but it's not so scary, don't worry. Okay, why is it not so scary? Because we are going to simplify it, to look at the patterns and try to make sense of it. Okay, so don't worry, in the next half we are going to go deeper into this and how we can simplify a truth table and come up with appropriate logic gates. Okay, so later I'm going to show one logic circuit which looks complicated. Don't get a heart attack. Okay, that will not come up for midterm. Okay, so don't worry about that. Okay, so now this is what we have. We have ALU op and we have function field. Okay, ALU op and function field, and we want to generate the ALU control. So this is the sort of 2 input that we have, and this is the output that you want to generate. Okay, how do we make sense of this? First thing we can see is for BEQ, as long BEQ is the only instruction where the ALU op, this is bit 0, this is bit 1, and this is bit 0. Alright, okay? You can see that BEQ is the only instruction where the bit 0 is set to 1. Correct? Okay? In all the other ALU op, the combinations over here, you do not see any possible case of the ALU op bit 0 being 1. Okay? Okay, wait on. Okay, so BEQ, okay, is the only instruction where the least significant bit is a 1. Okay, so this means that as long as I see that the ALU op bit 0 is a 1, automatically I know this is a BEQ instruction, correct? I don't need to look at any other bit. Okay, so that is the first thing you can do. The second thing you can do is, you can see that for your ALU op, okay, it is always 1 and 0, correct? Okay, so similarly, since the load word and store word is having low significant byte 0, okay, and all of this has 1, so I can ignore the 0 at the bit 0. So as long as I see the most significant bit is 1, okay, so if I just look at most significant bit here, only for this R type instruction, all this is 1. Alright? Okay? For all the other type instructions, it is 0. Okay? So as long as I know the ALU op bit 1 is 1, then I know it is R type instruction. If I know the ALU op bit 0 is 1, then it is a BEQ instruction. Okay? So by just looking at this, I can differentiate between R type and BEQ. And what else do you see? You can also see that my bit function field bit 5 and bit 4 is always 1 and 0. It's always consistent. Correct? For all the different type of instruction that I'm supporting. Okay, which means I do not need to look at it. Okay, in Boolean algebra, whenever we say X, means we say it's a don't care condition. Okay, don't care means what? That means whether it is 1 or 0, I do not need to care because it's always consistent. Okay, when you're trying to simplify, what are you trying to do? All things that are consistent, we discard. Then things that are changing, then we look at them. Correct? Because if it's consistent, then it's predictable. We don't need to keep checking it. Correct? So we know that bit 5 and bit 4 of my opcode are the most two significant bits, are always 1 and 0. Okay, for all the instructions. So I can ignore them because they're always 1 and 0. Now a few other things that we're going to look at. ALU control tree. So if I look at this ALU control, out of the 4 bits, the bit 3 is again always 0, correct? Okay, so of course some of you might ask, hey, if it's always 0, why don't I just make ALU control 3 bit? Alright, why don't I make ALU control 3 bit if it's always 0? Because we are only showing you a subset of the instruction. Correct? You have to remember this is only a subset. We do not even look at I type instruction with immediate value yet. Correct? Okay? We never look at jump instruction. We never look at a lot of other things. Okay? So the ALU control, the 4-bit is there because you still need to cater for a lot of other type instruction. Okay? Right now what we are doing is a very sort of reduced subset. Okay, so that we understand the idea behind it. Okay, so in this subset, which is only your load word, store word, BEQ, and your few R-type instructions, your ALU op bit 3 is always 0. If you look at bit 2 now, so this is bit 3, how about bit 2? Okay, so bit 2, there is some relationship. Okay, I'm going to show you the relationship, but do not need to worry. For now, for midterm, no need to worry about how we derive this relationship. In the second half, we will see. But for now, the relationship is given as this. Okay? And what do we gain by this? We say that this ALU bit 2 is 1 based on what? ALU op bit 0 or ALU op bit 1 do a AND operation with my F1 with function field bit 1. How do I get this? Okay? So for example, this one over here. Okay, this one over here. How did I get this one? This is ALU op 0. ALU op 0 is this one here, correct? Okay? So this is 0. Okay? So 0 does not make any impact to us. ALU of 1 is a 1, correct? Okay, ALU of 1 is a 1. So this is a 1. Do an AND operation with function field 1. Function field 1 is here. 1 plus 0, so the answer is 1. Alright, this is a 0 or with a 1. Okay, so the output is a 1. So the 1 that you see here is obtained or can be obtained by observing a pattern between ALU of 0 and ALU of 1. Okay, so don't worry if you think that it's a bit confusing. So we will look at this again when we look at truth table and simplification again, how to systematically do it. Well, right now it looks like magic, how I suddenly can come up with a relationship. So it's not magic, there is a systematic way to do it, which you will learn in the second half. So for now, like I said, just take it as it is. Okay, how this thing come about, the step by step we will cover after the break. For now, just take it that this is the relationship. Okay, so the main idea is what? The main idea is we do not want to look at all the bits. Okay, why we are doing all this? We do not want to look at all the bits. Why? Because if I look at all the bits, then I'm going to have to look at what? I'm going to look at 2 plus 6. So my total is going to be 8 inputs and 4 output at the output. Alright? Okay? Is it possible to do that? Yes, it's possible. Alright? But again, we do not want to introduce unnecessary hardware into your processor if you have an option to simplify. Okay, so all this step that we are doing is the process of simplifying your logic up front so that the hardware becomes more simpler. Okay, so this is your reduction table. So eventually, this is the design of the ALU control block. Okay, so just to give you a sense of how the relationship comes. Okay, so if you look at this, ALU op 0 plus ALU op 1 dot F1. Where does this come from? This is your ALU control 2, which is this. Okay, the 2 input is ALU op 0, which is coming from ALU op bit 0, and the other one is your op 1 here. Do an AND operation with my F1, and both of this is combined with the OR gate. Okay, that's how the whole hardware block comes about. Okay, so again, don't be worried. We will cover this in more detail after the break. Okay. So now, the final part is to look at the entire design. Okay. So what do we have? We have your whole processor, which we have seen. And what do we introduce today? We introduce the control block over here, and we introduce the ALU control block over here. And what is the purpose of these two blocks? The control block is to generate all the various pins over here. Alright. Now what do you see? All these control signals that we saw earlier, register destination, register write, blah blah, all of this has to be decided based on what? Based on just my 6-bit opcode. Correct? That means using my 6-bit opcode alone, I must be able to generate all these various control signals. Correct? My register destination, my register write, my memory write, mem to register, all these things. Okay? The 6-bit opcode itself should be enough to tell me all of this. Then I need to also generate a 2-bit ALU op over here. Okay, a 2-bit ALU op together with the 6-bit function field to generate another 4-bit ALU control. Okay, so there's two parts to it, correct? The 6-bit opcode directly gives me all the control signal. Then I still generate another 2-bit ALU op that will combine with my function field to give me the remaining 4 bits for my ALU control. Now let's look at the control design. That is all the output that we look at. Okay, so for R type, okay, for R type, what do you see? So all this we saw just now, correct? For register destination, R type should be, this is 0, this is 1, correct? Okay, so for R type instruction, the register destination should be 1 because the 1 should come here, correct? Okay, and for R type, you also need to do a register write. So register write should be 1, correct? Okay, your ALU source should come from where? Should come from your read register. Okay, so it should be, your ALU source should be 0, correct? Because 0 is on top. Okay, next is your memwrite and memread. Both of them are not being used, correct? Okay, memwrite and memread. So rightfully in a simplified version, okay, memwrite and memread should both be 0. Yes, in this case. Okay, in your branch, you are not going to do a branch, so your branch is also 0. Alright, so this branch here, this branch control signal will be 0. Okay, this branch control signal will be combined with your ALU output to determine your next PC. Okay, and finally your mem to register, this one should be 0 is below. So in this case, in a R type instruction, I'm going to take my ALU, correct? Okay, so this should be 0. Alright, and my ALU op should be 10. How do I get 10? Because I already preset that over here, correct? Okay, so for ALU op here, we already said that for R type instruction is 10, BEQ 01, and memory is 00, correct? So we already know that this is the required output over here. Okay, so it should be 10. Okay, so you can see that for each type instruction, we can know what are the different register value to be set and to clear, and what is the ALU op. Okay. Okay, for your load word instruction, okay, your load word instruction, for example, your register destination is 0. Okay, so your register destination is 0. Why? Because in your load word instruction, this is your target, correct? There is no RD in your load word, it is RS and RT, correct? So your RT is the one that should be transferred over, so your register destination should be 0. Okay, similarly, your ALU source should be 1. Why? Because in load word, you are taking the sign extended immediate value to specify your second ALU operand. Correct? Okay, so that is your ALU source. Then your load word instruction, you are going to read from memory, correct? Okay, so your memory read is 1, your memory write is 0. Your memory read is 1. Because this is a load word, you're going to read from memory. Okay, your branch is 0 because you're not taking a branch. Okay, and in your load word instruction, you are taking from memory and writing back to your register. So your register write has to be set to 1. And over here, you are taking the data from your memory and channeling out. So your mem to register should be 1. Okay, so all this is important. Important means what? Guarantee plus struct sure will come out 1. Okay, even though I haven't set exam paper yet, it sure will come out 1. Okay? Okay, and this one 0, 0, we know from your ALU op. Okay, so you must know how to take an instruction and figure out which register or which control lines will be set, which multiplexer will have what value, and so on. Okay, so the rest you can go through and see. Okay, so but you can see there are some of it which is X. Why do we put an X? So for example, in register in store word instruction. Okay, in store word instruction, we are going to take data in the register and write to memory, correct? Okay, so the RS is use a different color. Okay, so in your store word instruction, you have your RS, you specify, plus you also specify a RT. Okay, that will go here and also go here. Now, if you recall for your store word, what do? It is the data that come out of RD2 that get mapped directly to here. Okay, in a store word instruction, your RD2, okay, which is from your RT, is the one that is the data in the register that will eventually be returned to memory. So in that case, this register destination does not make a difference. Why? Because from here to here is already hardwired. Correct? The bits 20 to 16, which is RT, already go directly to read register 2, which will provide me with the data over here. That is the data that is going to be returned to memory. Okay, so whether my register destination is 0 or 1 makes no difference to me. It makes no difference. So that is why we say don't care. Why it makes no difference? Because eventually my register write is set to 0. Alright? So since my register write is set to 0, no matter what I specify as my write register, nothing is going to be written anyway. Alright? Nothing is going to be written. Okay, so that is how we play around with the use of your control signal, okay, to know when to use which signal for the different type of instruction. Okay, so you can see for yourself here. So similarly, mem to register, also we say don't care. Why? Because even though some data will come out of here, okay, some data will come out and come here, again, register write is still 0. Correct? So even though there is some data there at the right data, there is some bits there at the right register, my register write control signal is 0, which means nothing will be written anyway. Okay, so that is why we say don't care. Okay, so ALU source and all, you can look at that. Similarly for BEQ instruction. For BEQ instruction also, we say don't care for register destination. Why? Because your two registers that we are comparing is already in your read register 1 and read register 2. Okay, so those two registers will come here for us to compare. And similarly, register write is 0, so I do not care of mem to register value. Okay, and for BEQ, the branch is set to 1. So this branch is set to 1, but I still need to wait for my result of my ALU. So the branch set to 1 doesn't mean branch is going to be taken, correct? For me to take the branch, two conditions. One is branch set to 1, and the comparison must say it is equal. And comparison must say it is equal. Then I say that the branch is supposed to be taken. Okay, so that is the importance. Okay, so these are all the different type of opcode that we have seen, okay, for the instructions. And from this 6-bit opcode, okay, from the 6-bit opcode, I must generate all these pins. Okay, so now you imagine the control unit has 6 input. The control unit has 6 input, which is the 6-bit opcode. And for the 6-bit opcode, I must generate how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 output. Okay, 9 output from 6 input. Okay, so these are all the different opcode that I need to handle at the input side. And from there, I need to generate the output. Okay, this is the one I said don't get heart attack. Wait first. Okay, so you just take it as it is first. Just take it as it is first. We will look at how it actually works a bit later. But just to give you an idea, this one is what? This is an AND gate, correct? All these are AND gate. And all these at the other side are OR gates. And effectively, what do you see here? We are just trying to directly map all the inputs to all the outputs. Okay? So for example, here, if I look at this, my R-type instruction is when all my inputs are 0, correct? Okay, so how do I do that? I can just have an AND gate where I put a bubble in front. When I put a bubble in front, that means it is active low. That means I want to see a 0. I want to see a 0. Huh? So effectively, what does that mean? All the bits here must be 0, 0, 0. Then this output here will become a 1. Okay, and this one goes to where? Your register destination, correct? Okay, and for R type, should register destination be 1? Should be 1, correct? Okay, so that is how you translate the truth table to the hardware. But anyway, if you don't understand, this is okay. You don't understand, this is okay. Don't worry, we will go through this again in more detail. For now, take it that this is the translation of your truth table relation to the actual hardware. Okay, so your input is the 6-bit opcode, and the output is all the pins that you want to generate your control signal together with your ALU op signals. Okay, and effectively everything should be completed, okay, within 1 clock period. Okay, 1 clock period. So when I have a clock that is applied, that means my instruction is fetched and sent to the processor. It should complete the whole instruction before the next instruction comes in. Okay, so this time that it takes varies, correct? Okay, so let's look at a few, just a simple example here. If I have an instruction that is purely using ALU, that means only R-type instructions. Okay, then what do I have? What are the different access I need to do? The first step I need to do is I need to access instruction memory, correct? Why? Because I need to fetch the instruction from my memory. After I fetch the instruction from memory, I need to read from my register. Correct? That's the second step I need to do. Third step, I need to activate my ALU. And after I activate the ALU, I get the output. The last step is I write back to my register. Okay, so if I were to look at the R-type instruction, I have a total of 6 nanoseconds of execution time, for example. Okay? Whereas if I were to have a load word instruction, okay, this instruction memory is consistent for everybody. Correct? For register read, it's also consistent for everybody because all your instruction will have at least one register involved. Correct? So definitely there will be instruction memory, there will definitely be register, and there will always be ALU involved. So these three are common across all these type of instruction. Data memory is only accessed for load word and store word instruction. Okay, and register write is used whenever I need to do a R-type instruction, which I will write back to a register, or I do a load word instruction where I take from memory and write back to register. Okay, so you can see that the one that takes the longest is the load word. Why? Because load word has to practically access all the elements, plus it also has one more final write back cycle here. Your store word also access everything, but after it writes the data to the memory, there is no write back to register. For your load word, after I access memory and get the data, there is still one final write back to my register. And that is why you have one more cycle here. Okay, so you can see that for your processor, your memory access will always be the slowest because it adds additional cycle time. Okay, so which means what? You can only clock your processor as fast as your slowest instruction, correct? You can only clock your processor as fast as the slowest instruction. So this will be the bottleneck of your processor's clock speed. Okay, so if I want to clock my processor, the fastest I can go should be 1/8 nanoseconds. That is of course the theoretical fastest that you can clock, for example this processor. If I clock it any faster than this, it means that some instruction cannot complete in time. Correct? So how do I make it faster, make it better? So there is two ways of doing it. One is called multi-cycle. Currently we are doing a single cycle. What do you mean by single cycle? That means in one clock cycle, I do everything. Okay, that means in this clock cycle, what's the first thing that happens? The PC is sent to my instruction memory to fetch the instruction and send to the processor. And from there, everything starts, correct? Everything starts until it finishes. So what is the worst case scenario? The worst case scenario in this case we saw was 8 nanoseconds. That's the worst case scenario. Okay? So in a multi-cycle, what do? I have a clock for different sections of my processor. Okay, so we say that each step takes one cycle to execute. Okay, so your frequency can be much higher. Okay, the drawback is in a sense that you have different instructions with different number of clock cycles, so you need to be careful of how you manage that. Okay, so it's a bit complicated and we're not going to cover that in class. What we're going to look at is pipelining, because that is the direction of all the modern age processors, where you allow multiple instructions to be in the processor at the same time. Okay, but in different stages. Okay, this is in the later lecture. Later lecture means towards the end of the semester. Okay, we will come back to visit MIPS again. MIPS will come to haunt you again and again. Don't worry. So you will see this again towards the end of the semester. Okay, so to summarize, today basically what you have done is we have effectively completed the entire processor. Okay, from the different stages, from the moment you fetch your instruction all the way to analyzing the flow of data in the register. And today was the control block. Okay, it takes time to analyze and understand everything. Okay, so all this flow, so this example, this kind of flow of data, a different type of instruction, what will happen, how will it flow, it takes time to read and understand and appreciate. Okay, so if you don't quite get it immediately, it's fine. You must go back and try again. Okay, so for your midterm, okay, it is all the way up to this topic. Okay, but listen, relax. Okay, but this tutorial is only covered after the midterm, correct? That means it's only in week 7, then this tutorial is supposed to be scheduled. Okay, but of course I'm fair to everybody. So what I'm going to do is, I'm going to cover the tutorial tomorrow in class. Okay, so tomorrow in class, the lecture is going to be tutorial 5. Okay, so when you come back after the midterm break, okay, that week is for you to consult with your tutor on all the topics that was covered. Okay, and for you to revise whatever you want. Okay, so this topic, okay, is considered part of it. Okay, but I will only set at most 2 questions from this. Until the previous lecture, it will be the rest. Okay, wait, let me talk a bit about the midterm first before you go. Okay, before I talk about the midterm, we will have one Kahoot quiz first. Trust me, you want to do this. Trust me. If you do it, you will be happy next week. Next week. That's all I can say. I need to go and check. Okay, so the Kahoot quiz is more on the MIPS programming, to make you revise your MIPS programming. So you have done your lab, you have done some exercises, so you should be able to sort of answer the questions. Okay, anybody else? If not, we will start. Okay, so the question asked is after line 2 is executed. Okay, so line 2, so the first line, what does it do? It loads, LA is what? LA is a pseudo instruction to load the address of either address of a label to a register, correct? Okay, so when I execute line 1, the address of where this is stored will go into S1, correct? This label value here. Subsequently, I'm using an indirect addressing, so this is the offset. So S1 plus 0. So S1 plus 0 is this address, the first word here. So since I load a word, this whole word will come into T1. Okay, so that is why you have FFAA1122, which is your first 32-bit value here. Okay, so all this is taken from your Qt Spim only, so you can try it out, all this kind of simple code. Okay, so those who got it wrong, I assume you cannot see. I assume you know. Maybe you cannot see from the back. Let me see what I do. Okay, so about slightly more than half. Okay, so what was the question? The question asked you, after line 5 is executed, what is the value in T1? So line 5 is here. So what are the things we are doing? Okay, we are loading FFAA1122 inside T1 register, and we are adding it with 0, putting back into T2, correct? So eventually we are just copying T1 to T2. And then we are doing a shift right operation by 16 bits, correct? Okay, that means what happened? The lower 16 bits will disappear, correct? Left is the upper 16 bits. So the FFAA will move all the way down to here, and upper 16 bit will become 0, correct? Okay? And then over here, I'm just doing an AND T1 with FFFF back into T1. So it is nothing more than keeping the FFAA at the bottom, and the upper 4 hex is 0. Okay, so that is what we are trying to do here. Okay, so we're just carrying on. So over here, T1 is already having 0000 FFAA, correct? Then T2. T2 is holding the original value of this, correct? Okay, so the 1122 is there after I do the AND operation. So when I do the AND operation, I'm keeping the 1122 and I'm discarding this, correct? And then I shift left by 16. So the 1122 will come to the upper half, correct? Then I do an OR operation. Okay, so effectively what I'm trying to do is I'm flipping around the lower 4 hex and the upper 4 hex, correct, from the original data. That is what the whole code is trying to do. Okay, so that is what. Okay, last question. Which instruction will load the value this into S2 register? Okay, so about half got it right, half got it wrong. Actually, this is the easiest question. This is the easiest question. You know why it's the easiest question? Because when I straight away look at all these three, it's impossible, correct? You cannot specify a 32-bit immediate value. Correct? So you should immediately know that the first three instruction is already not valid. Even if you don't know what is this, you hantam sure get correct one. Okay? Because you know that the immediate value cannot be 32-bit. Okay, so the first three are invalid. Li is a pseudo instruction. If you look in your, I think you've used in your lab as well. If you type in Li, but when you compile, it will actually translate to two different instructions in your actual pure MIPS. So this is to load the immediate value into your register. Okay? So we have a MIPS. Daddy. Okay, unfortunately, I forgot to bring the chocolate for you. So whoever you are, who is there? Who is the winner? Okay, tomorrow you take from me. Today I forgot to bring. Okay, so before you go back home, okay, so midterm overview. Okay, I will post this on announcement. Don't worry. So don't you take photo. I'll post on announcement later. So it's closed book, approximately 30 questions. Okay. Why approximate? Because it depends on my mood during the 1 week break. Can be more, can be less. Okay, suddenly I'm in a mood to set a lot of questions, can be a lot suddenly. Time is, I think should be 1 hour 30 minutes. Okay? Okay, so all answers to be on the OCR form. So you must bring along 2B pencil and eraser. Okay, please don't raise your hand and say, can I borrow eraser for my friend? No, Okay, you must return the question paper as well towards the end, because some of your friends who can't make it for the initial one will come for the later one. We will provide the MIPS instruction set, so you don't need to worry about that. Okay, all material covered in lectures, tutorial, and lab. The programming concepts will be covered. Okay, those things in the lab, such as your value for your system call, all that, of course, we will not ask. Okay, the programming concept for C, for MIPS, those programming concepts we will test. Not those Qt spin specific, what is the system call, all these things we will not ask you. Okay? So just to give you an overview so far what I have set. I have managed to set 18 questions so far. Okay, 3 questions on number format, 8 questions on C programming, 7 questions on MIPS. So 18 there. That means the remaining 12 should come from where? The other remaining part of the MIPS, correct? Which is your data part and your control. Okay? So again, this is non-exhaustive, so you will still proceed over the next few days and the following week. So I will update you all through announcement on the final set of questions that will come out. Okay? So tomorrow we will go through tutorial 5. Okay, the question already is uploaded. Tomorrow I will go through, then I will release the solution for tutorial 5.
what we do is we convert the case A, B0 becomes 1 and B1 becomes 0, right? Then we do add. So what is A0 and B0? And we want to subtraction.
It will still be 1 after you complement the 1 and 1. Yeah, after you invert.
If we do A minus B and A is 0, B is 0, we should get 0, right? But if we do the change, then it becomes B becomes 1, then we do add, then the result is 1.
No, it becomes 0 carry 1.
0 carry 1?
1 and 1.
But we don't flip A1, we only flip B.
Okay, so 0 minus 1. So it's 0 plus. So it's effectively 0 plus 1.
Yes.
Correct?
And the result is 1,
Correct. But then you still have to do the final complement.
which is what is the final?
The final complement will be based on the two's complement. I mean, effectively, okay, if you look at it bitwise, 0 minus 0, correct, is equivalent to 1 minus, is equivalent to 0 plus 1. So when you add the final carry in for the two's complement, then it will become back to 0, correct? Because you need to make the final answer two's complement again. You know the actual value.
At first we went to complement. I thought we just took the number and then we took the very last bit and then we process it into the simplified. Yeah.
But then that is the raw data, right?
Okay.
A and B. So, but to make it two's complement, I still need to, after the B invert, I still need to add one more one, correct? Carry in.
Okay, but then you get 10.
If you 1 plus 1, 0, carry 1.
Then you carry 1 over.
Alright. Eventually the answer is correct.
How is it correct though? Like,
Yeah, correct. Because eventually it's 0 minus 0 is still 0. Right?
yes.
Then the 1 carry over. Lah.
Okay, so suppose that I pass in two numbers. The first number is just all zeros, and the second number is also all zeros. So the processing unit will take the last two digits.
So eventually it becomes 0 and 1, correct?
Yes.
Then you add in the carry, correct? To get two's complement.
So whatever result, we just always add 1 at the end.
Your carry in has to be 1 because it is a subtract operation. Alright?
Okay, if it's a subtract operation, it has to be 1.
If it's a subtract operation, then you carry in from this to 1.
From the first digit,
From the last bit. Yeah, least significant bit.
from the least significant,
Correct.
from the least significant
So,
bit.
so in your situation, with all zeros and all 1, then when I add the 1, then it becomes 1 plus 1, 0, carry 1, then it becomes 0, carry 1, 0, carry 1, for all the way, correct? So usually the answer is 0.
Okay, so you're saying the last bit has a carryover of 1 and it gets split to 0. That carries 1 to the next one, which causes it to flip, and all of them flip accordingly. And then the very last carry just happened to match with the first carry to the
The
missing
very
bit.
last carry in this case will you can use it to check whether there is overflow condition or whatever lah. But the answer will be correct.
In the tutorials, right, the answers it says so using all the non-pseudo instructions. But which one is more preferred or which one is needed?
Generally, I mean the question, if you are asked to write code,
Don't use the
you
pseudo.
will specify whether pseudo is accepted or not.
Good example. Okay.
You will specify whether you use pseudo instruction or you have used pseudo instruction.
Can I ask, right, for the last week's lab, there's this question about the hello appearing on the asking value. But why is it like reverse? Like L, L, E, H, then another 4 empty, 3 empty space, then O.
It is the addressing because your H will be your lowest address, correct?
Yeah.
Correct. So your H, see when you put HELLO, correct? This is the lowest address, next address, correct? But in your future speed, when you see the memory, that is one word and next word, correct? That's how the key system displays the memory content. It's word by word, correct? So in this word, it is in that one word, this one is the lowest significant.
Oh, so it's like 1, 2, 3, 4, then another one, 1, 2, 3,
Correct,
4.
correct. That's how
So
it
you
is.
are right on.
That's how it displays the data. But if you just look at memory, it is one continuous one, correct? But the memory is displayed as word by word, and each word is lowest significant byte, most significant byte.
So it's 4 by 4.
Yes,
Then,
that's how
okay.
it is.
Okay.
为什么 reverse？
Yeah, so for example, what did I say last time?
Forwards. Lowest significant bit 是在 right side. So the midterm is 在 left side. Then it's 4 by 4.
You mean the most recent
So it's
one?
low to high, low to
The
high.
most recent one is applicable, correct? Sem one.
last year Sem 1.
No, basically you only look at the latest one. Anything before that,
Most. HELL,
I'm still confused about where the one carry over comes from. So you have a bunch of zeros plus a bunch of ones. You have a number of zeros plus a number of ones. And somewhere, somehow, a one comes in to set all of them to zero.
so for example here, so the question is 0, let's say 4 bits.
Okay.
Okay, minus 0. So answer, so it is 0 minus 0, correct?
Yes.
Okay, so this 0 is this one, and minus 0, correct?
Yes.
And this one, I need to specify as 2's complement, correct?
Okay. Yeah.
So this 2's complement means I flip, correct? Plus 1, correct? Okay, so you're talking about the actual hardware, correct? What is
Yes.
it?
Yeah.
So this one comes in here, correct? Okay, so let's look at bit by bit. Okay, so I have 0, subtract 0, correct? But since this is a subtract, correct?
Yeah.
This is plus 1, correct?
Yes.
Okay. But this is 1's complement, so I need to have one more carry in, correct? It is another 1 for the least significant bit.
How do you calculate this one?
Because this is a subtract.
So wherever there's a subtract, there is a one carry.
Because it's 2's complement,
Because it is two complement.
2's complement is like invert plus 1, correct?
Yes.
So this is invert, then I must still have a plus 1.
So wherever you subtract two complements, you always invert them plus one.
No, I mean numbers of the relation, what do we learn? We learn that 2's complement is original bit flip plus
Flip
1.
plus one, yeah.
Right, that's what I'm doing. So the least significant bit, after I flip, I must add 1.
Okay.
Correct? I mean, if I ask you to give me a 2's complement, what would you have done? You would have flipped and add 1, right?
It will still be all zero. Yeah.
Correct? You would have flipped and add 1, right? That's what the hardware is doing.
Okay.
So you flip and add 1, correct? So what's the output here?
Zero.
0,
Carry over one.
carry over 1, correct? So this carry in becomes 1. 0 plus 1 plus 1. What do you get? 0.
Zero. Carry over one.
Carry over 1. So eventually what do you get? 0, 0, 0, 0, and then the output is a carry out 1.
Okay. Then what happens to this carry over?
So it's up to us to see whether the processor will look at it and trigger it as a overflow condition or carry out or whatever. So in this case, if the processor will have certain flags in some processors to indicate whether it's a carry or overflow or whatever.
Okay.
But in this case, since it is, you will see that the carry in and carry out, I mean we have not covered this yet, but basically in this case, the carry in to the most significant bit will be 1, and the carry out will also be 1. So in this case, there is no overflow condition.
case, this is just the last bit after the condition. That means your answer has